title of the talk is Continuity of the Dimensions, Harmonic Measure of Autonomous Conformal IFS C.
Thank you for the invitation. Yeah, I try to put up a talk of 1.5 hours. I'm not even certain to be able to hold that long. I suggested to Felix to have a complete with jokes, but he wisely declined my offer. Okay, so this is a joint work with Guillaume Havara, and in fact, part of this work has been done in IMPAN many years ago. And then I somehow had a break because I got some political responsibilities, and then we finished it last year. So I'm also glad that there are young people here because there is a part of this which is well known by at least the more experienced of you, and so I apologize for this well-known part, but as somebody said, never underestimate the pleasure one may take hearing things he already knows. So, okay, so there is this, a wrapping of the talk. So the beginning will be the easiest part, afterwards a bit more technical. So to start with, what do we call a pattern? The pattern is, in fact, what you see here is the blue, these blue areas. That is the unit disk. Inside you have some simply connected domain Jordan curves that are disconnected, and then of course you have the conformal maps that send these blue curves on the unit disk, and these are the phi maps, and the psi maps, the contrary, send the unit disk onto these blue domains. So we do the hypothesis that our conformal maps are defined in the neighborhood of the disk, which is of course sent in the neighborhood of these blue domains. This I will call a pattern. Now, the degree of the pattern is a number of subdomains. Here, for instance, it will be 3. And the main idea is that, so that's what I told before. Before we ask for the conformal maps to have this property, which means that don't shrink too much and we stay, how say, away from the disk. And of course, I told you that the domains are pairwisely disjoint.
Excuse me, what about the boundaries? Are you assuming that boundaries are also disjoint or not?
Yeah.
Okay. Those separate.
I simplify the maximum. There's probably, I can do things even if they touch, but it will complicate something that is already too complicated. And don't tell me that that's what the mathematicians do, complicate things that are already complicated. So, okay. So what would be the zoom application would be so the application tree that will send all these 3 domains, for instance, each one of the 3 domains to the circle. Okay. Okay. Now, when we have a sequence of patterns, we can define in the usual way the Cantor set that goes with the IFS, I will call it IFS. So, the diffraction system. Okay? But the term of non-autonomous means that I don't use the same pattern all the time. I allow myself to change patterns. Okay? this is what Guillaume do, like painting. So take to his slide. So here you have three patterns, and then of course, by applying successively the iteration of the function, you go from there to there. These are things that probably already everybody knows well. But help me win 5 minutes. Now, okay. This is the definition of harmonic measure through probability on small. I think that everybody knows it. So we can, when we have a domain, not only an autonomous IFS, but a domain, we choose a point in the domain, we start drawing motion at this point, and the harmonic measure of any subset of the boundary E would be the probability that Brownian motion exits the domain omega through E. Okay.
When you say X is an autonomous FS and write C hat minus X, what do you mean?
Sorry.
X
X
is
it's
limit set of
he lives here and he hits X for the first time at E. Yeah. So of course there are several things to. So this is a probability way to define this measure. This is a probability measure whenever you have a domain, a boundary each of positive capacity in R2, which is not the case in R3, but we will work on C, no R2. So we have a probability measure. This measure depends very little on the point you chose Z, because by Harmonic, sorry, the next slide. Yeah. So this function here, so when you fix E here, sorry, when you fix E, this function here is harmonic, which is 0 outside E and 1 on E. So by Harmonic principle, if you take two different Z, the values of this function are equivalent with some constant. So that doesn't really depend on Z, this function here, this measure here. And yeah, this is standard notation for this measure. I'm cheating, saying that I make the Brownian motion start at infinity. One has to do some job to be able to say this, but it's not very difficult. Now, sorry, I forgot to say that, as we probably well know, the harmonic measure is, of course, a conformal invariant. Now, I said I will speak about continuity, so I have to find some metrics. I take two non-autonomous IFS that have, so remember phi is the dilatation and the psi is the contraction. So I take two IFS with the same sequence of degrees, that is, the patterns at every step have the same number of domains. Okay. And I define this metric, which is really metric, never mind, this pseudometric, let's say, it's just the infinite norm of the difference of the psi's. Now, since I have this neighborhood around, this fixed neighborhood around this, if this is smaller, I will get the same thing for the derivative also. Okay. That was this one. So yes,
when you take the supremum, you take over all, when you take normal, you take all over neighborhood, or not just over the disk, right?
take it just on the disk. So that's also it's sufficient. I think the closest. Yeah, but I have a remote. Okay, yes.
So early on, you assumed a bound on the e-type thing it was, so the bound on the derivative. So is this bound given along one branch or along all possible degrees?
No, it's for every contraction.
So it's absolutely universal.
For every, yeah. That is the neighborhood and the bounds are fixed. You shouldn't ask me this question. I think how if we can get better than this now. But yeah, for the moment, suppose I fix. So usually also how say terminology, Hausdorff dimension, Batakis dimension, and then the theorem I propose is the following: with this metric, the dimension of the harmonic measures that go with the set X are continuous. So that is, if X and X tilde are closed, the dimension of harmonic measures, both dimensions, will be closed. I don't know if I have more than just continuity. So, okay. The main thing that we have up again and again and again is that we have non-autonomous sets, and so we have no limits. Okay, and whatever happens, the main problem is to at least be able to identify a subsequence that will give you the good dimensions over all we have to do. And when I have the overline, the upper line for the pressures, for the pressure functions, it means like limit inferior and limit superior. Okay? And yeah, this is well known. I think that even Anna worked on it, Marisol Bansi worked on it. So in this case in this framework, the Hausdorff dimension will be the zero of the lower depression and the Batakis dimension of the higher depression.
Lost. What is pressure on the measure? Pressure is supported.
But how it will be defined?
How it will be defined?
I wanted not to define because I will not use it. But if you want, I will give it to you in a second. So. I just put it because I thought that everybody worked with pressure here.
This is something not standard pressure with respect to a measure. So this was a question.
Could be topological pressure.
That's what
parameter being.
it's
No, but
said.
then it doesn't correspond to the network.
Then it is zero. This is.
I answered this again. We don't need it. I don't use it. Okay. So. So I go past on this slide. Yeah, I have to tell you that I use the slides of a presentation that I did Guillaume, so I have written them a lot.
Part is in French, the strategy.
It was in French, yeah. It was very, very long and very, yeah, there were things that I would want to talk about. Now, for this part, okay, that should be no things to clarify. So, what is known for harmonic measure, just to put the framework of the work, these are all the now results, classical results of Makarov and Peter Jones, Thomas Wolff. So, the dimension is always smaller than 1, equal to 1 for simple connected sets. And then there are all these works of Carlson, Warburg, Makarov, Anna, Rymansky, that worked on conformal and autonomous IFS, and I don't know why it's written 2 times, because probably I forgot to erase it. And for non-autonomous sets, there is a work of mine of Anna, but this is not for conformal maps, just for similarities. Okay? This is an open question for a long time now. When you have a conformal IFS, even if it is the same pattern, you always have this inequality, okay? which is still not known. The rest of the knowledge. There are some partial results of Borger, but further assumptions. Now, there was some kind of early conjecture at the time saying that whenever we have a disconnected set of small dimensions, necessarily we have this dimension drop between dimension of omega and dimension x as before. This inequality was supposed to hold even for non-IFS control sets, but we know for a long time now that this is not the case. Christopher Bishop has allegedly given another example, but he never published it, so they don't know how it is of the same type as mine. So just 2 words, because things are interesting. Okay, have a dimension. Can we say something about the measures? Can we say that whatever happens, harmonic measure and Hausdorff measure in the right dimension will be singular? Now, there is an example of David Pesna, the promise right, and Julia last year, in last year's paper, where they constructed a Cato set of small dimensions, photon, where the 2 measures are equivalent. Now, what is true is that this is not an IFS, since we have still the conjecture that we have the dimension drop. Okay, if this was true for an IFS, of course the dimension could be. This is not an IFS, just a Cato set.
Sorry, one second question. So for autonomous IFS, there are no example nodes for which you have.
For autonomous IFS, that's an open question.
I see.
For non-autonomous also. Okay.
So this dimension is the Hausdorff dimension? Or
Hausdorff dimension.
So is this question relevant for the packing dimension?
Yes, of course. That is yes, of course. There are not many things that have been done for packing dimension. In fact, when you have autonomous IFS, the 2 dimensions are the same. So in the non-autonomous case, you have this. Okay, let's go to this. Okay, so there is something that's very. I put this slide because there is something that's very surprising here. There is a very recent result of Xavier Tolsa saying that if you have a totally disconnected, Cantor set with some very mild hypothesis of dimension greater than 1/2, then you cannot have this relation. So whatever Tom Julian did last year, they had to go seek things in very small dimension. Okay. I think their method goes up until 1/4. So, just to say that it can be tricky, these things, and you can imagine that, yeah, generically have this or that. No, it is. Okay. Now, in whatever is the multifactor formalism or thermodynamical formalism for non-autonomous IFS, there are many works that have been done, and this one is used in our paper. So just to complete what happened in the area recently. Maybe I forgot some, but it's probably I forgot some. Now, a few words on symbolic dynamics. First, we have all our sets here, and we have to use to send them in this symbolic space, so which is rather natural, rather standard. So I still use the paintings of Guillaume because since he did it, we as well use them. So to define things properly, we have a sequence of patterns, conformalism, and degree. Of course, if you have the conformalisms, you have everything, but never mind. We define by induction the IFS that goes with it, the Cantor set that goes with it. The sequence of compact sets that will create a Cantor set this pattern. Okay. And we will code it in a very usual way. Okay. We'll use alphabets with the number of symbols, S symbols as the degree of our patterns, with the product of this alphabet, and then, of course, we will, for some reason, very soon when it was in the slides. So, it's an easy way to identify now the sequence of the coding space with the, the copies of blue domains we have at the nth step of the construction. Now, once more, this very standard, we know things that shouldn't spend time on this. This is something that is very useful, that is and then missing here. So this is very useful, this contribution to the shift. But the shift is not a good tool in our case. Because when you go from one generation to the other, everything changes. You don't have the same patterns. So you cannot hope any invariance. So we have to deal with this problem. But nevertheless, the coding is central in what we do. Next. Yes. Okay. So, I'm not that heavy. So if you have a window, that we call this a window, you have so your coding, the decoding of every point of your set. You take a window, a fixed window, you go from AK to AK plus n minus 1. I will call it a K cylinder of length n. These objects, which you have to imagine them as something that is in your sequence, it's a sub-cylinder, a finite sub-cylinder. will be used all the time, of course. So that's why. Okay, so the notation is rather, how to say, natural. It is as everybody thought would be, that is X is just the intersection, sorry, the image of E by this subcylinder, and then this X will be exactly the subcylinder. So we identify X and X. So, okay. This is true in general for measures that we use all the time. That is,
Depends on the meaning of this
yes.
person before.
Well, no, it's even also. Generically, at least we hope that this thing is true for almost all X. Okay, and the main thing is this here. Your delta in the autonomous case, or in the all the reasonable cases, this is true for almost all X. Okay, and at least at the limit. Now, in the non-autonomous case, this delta of X is delta R of X. This changes everything. Okay. Now, I will write down whatever we know here, that is in general cases. Suppose that this is true, we get trivially, almost trivially, almost. Okay? The delta of X, of course, that belongs here will be something like this. We write like this also. You can define the local entropy of mu at X, which will be just one n. Sorry, the limit of these guys here. So it's this guy over here, and the local entropy of this guy here, the limit of the limit, and the local dimension. Now, I put in
do you choose a sequence of?
no. That's what we hope in general. That's it. This is not true in our case.
No, but I forgot whether it's probabilistic or just autonomous or no.
In fact,
So did you fix some sequence of
no.
IFS?
That's
Just the same IFS all the time.
I think the question is what is the meaning of X and of X?
Yes.
Yeah, okay.
Random or it
I
is.
think this is the cylinder of orbital and
Whenever you have an IFS, you take a cylinder for. Whenever you have an IFS, you take the cylinder for the n.
Yes, but this is fixed IFS
Yeah,
or random.
this is not. I don't take any random IFS. All fixed. All deterministic.
but
Deterministic.
autonomous
Yeah.
autonomous or non-autonomous?
Whatever it is, this has a.
Doesn't matter, but it is fixed.
It's a fixed
Random.
IFS,
No.
and I have. This is just definitions. Okay? No, the only thing is that I put a very calligraphic limit here, because in general, in our IFS, we don't have a limit, we have a limit superior and limit inferior. Okay? So the calligraphical limit means whatever you decide it to be, limit superior or limit inferior. So you have H bar and X bar, and you see what I mean? If you take limit superior, you have a bar here, if I limit inferior, a bar here, etc. So I just use the two non-tools, that is.
Excuse me. So this is for almost all X?
No, this is a local dimension. For every X, you have this guy.
Small x.
Small x, yeah. Okay? This is small x.
My question was whether capital X is random or fixed, whether the sequence of ANs is random or fixed.
The capital X,
No, again, the question goes back to the sequence of IFSs. When
Okay.
it is fixed for
Fixed, yeah, that's fixed.
Fixed.
That's fixed. You
It's not
choose a
random.
sequence of
You
patterns.
choose sequence
you-
of patterns.
yeah.
Okay.
Yeah, no random pattern, no random. Okay. Take one IFS and no. Okay. So now,
Non-autonomous, but fixed.
yes, now starts the part that will interest us today. Okay. We can define, and we will define, we just did it, this entropy of the n approximation of entropy, let's say, this is the sum over all the cylinders of, sorry, the average of these quantities over all the cylinders. The average of log 1 over x over all the cylinders, the average with respect to the measure mu. This will give me something that normally goes to the entropy, but here it doesn't because there is no limit. Okay? And of course, the same thing we've done with Lyapunov exponent. Okay? So my tools today will be these two. Okay? These are my enemies or my friends. And the main thing I have to prove now is one of the main tools to just be able to work on continuity is some kind of Manning's formula. Okay? Okay, let me explain what I want to say right now. Now, I should have started with this, and I'm sorry, and I apologize. Whenever you have a measure, the Hausdorff dimension of the measure is the essential limit failure of the h of log of mu over the essential limited figure, of this guy. Okay? So this would give me, if the limiting infimum, they take the essential limiting over all x's with respect to the measure mu, this should give me the Hausdorff dimension. Now, the main issue is that suppose you have measures that are very close. That is, take mu and mu tilde that have the same, almost the same mu of x and of x. In the sense that if you go from one cylinder to the other, the ratio between the two, the fragmentation is smallest, or 1 minus epsilon plus epsilon. So suppose that this is close for two measures, mu and mu tilde. Can you conclude that the dimensions are close? Of course, if these are close, for every x, the limit and limitation will be the same, or almost the same. But since the two measures may be similar, it will be similar probably, the interest one is not the same as interest the other. So you cannot just say, okay, I managed to put this close, so I'm over. It won't work. Okay? You work with different quantities, with similar quantities but with different sets. So,
let me say how I understand it. Usually one background is shallow given very much lower, but then you have fixed partition and you repeat the pattern of the partitions. Now, more geometric is that you don't use partition, but just you switch to disks, smaller and smaller disks.
I know that's the problem. That's the problem.
And then what you are doing, you have different methods to construct sequence of partitions.
Yes.
So if it is okay for this, then what you are doing should also be okay by some unions of stationary sequences.
There are no stationary sequences.
So it starts from Shalom and then.
There are no stationary sequences.
Pardon?
There are no stationary sequences.
No, but I say from the beginning you have Shalom membrane when you have.
I don't have it.
No, but when one goes to disks, then one can forget about partitions like okay, that was my comment.
Yeah.
So I understand.
Yeah. To be able to do this, you have to be able to use a shift. Invariant somewhere. You have no invariance here.
This is starting point of it.
Ah, okay, yeah.
Then you switch to non-stationary. And there is no surprise at the end because you can build your finer and finer partitions by different methods, by non-stationary.
Not check. Check. Don't worry. Okay. Now, I shouldn't have do the reminders on what happens in the good case because maybe it's not the. I just want to show what the problem is. Okay. So I have just to avoid having very long formulas. I just use these notations, which will be the case that which will be the to simplify notation. Okay. So this guy will be just the house.
Excuse me, what is the xy?
Oh, something completely different.
Yeah.
Cylinder is.
Is it a connection or?
Yeah. Exactly.
Okay.
Okay. So you take a cylinder X.
Yeah.
The problem is that, of course, you have to be careful. Okay. You cannot put any cylinder Y behind any cylinder X because since you have at the beginning, for instance, three three domains, and then two domains, and four domains, and three domains.
Degree may not work. So you have to get like.
Yes, you have to put the right one. Okay.
More like a subsheet.
Yes. So, but you can still, if you have a big cylinder, cut it in two. That's what I'm saying. Now, and what I will call that's a how's it, a terminology. Okay? I say that a measure is beta n asymptotically invariant, invariant if whenever I take two cylinders of the same generation, so that's why I did this on the blackboard. Let me 3 here. Makes me win some time. Okay. Now, so the main idea is to say that the following thing that okay, I don't think this is shown on the blackboard. So you compare this measure to the measure of his father, and you compare this measure to the measure of his father. Okay. Now, if
What is Z?
sorry.
Z, what is Z?
Z is a subcylinder, a common subcylinder. So, okay, we are.
But Z, but these are completely different, they're located elsewhere, so.
They're located in the same place. This is just notation. Okay, this is u x y of z. This notation means u x y of z.
Of X or
That's
Z?
u of x y
Okay,
z
now I understand.
over mu of x y. Okay.
Okay.
Now let's see. Take this guy, and compare this. So let me compare this to that, and I compare this to that. So what happens is that this is the first the same alphabet copy of this set, okay? And then I take the same subset for both of them. Is clear what I mean? No, not here. So you have, okay, let's suppose that's C1, this C2 that gives you this one, and then you have C, let's say 1, 1. You have here C, it's the same one that goes here, okay? You see what I mean? It's C3 here. Here you have C3 also. You have taken the same interaction. And then you get in here, you get C4, but here it's also C4. So what changes is that are the grandparents, but the parents are the same. Okay?
This is supposed to mean something that whatever grandparent you take, children in nth generations should be close to each other.
Exactly.
So Sullivan calls it scaling function for maps of interval. You have x and x tilde, let's say interval, and you take tail. Then the ratio stabilizes. You have logarithm.
The ratio stabilizes.
You have logarithm. So if you start with Cantor set already, then you obtain in the limit Cantor set, depending on the tail going backward, you obtain some limiting Cantor set and limited proportions. And Sullivan calls it scaling function. So this is terminology.
Sullivan doesn't.
And I describe it carefully for maps of interval in my book with Urbani.
Yeah. Okay.
But I think this is about something else.
No, this is because these are measures. But the idea is that we have something in the xk, like x and x tilde, some generation cylinder, and then we choose the same past, and the ratio of measures stabilizes, heads to something.
Here it doesn't tend to anything.
Yes,
here it doesn't tend to anything, but you have.
But the ratio tends to
But you have the same type of oscillations everywhere, so you can do these things. Okay, but never mind. Just for able to fix ideas, take beta n equals to 0. Beta n take equal to 0 all the time. Okay. What we get will be what we call a Markov measure. Okay, that is every time it's your father that decides what value you will distribute, but not the grandfather. Okay. This is not really a Markov measure, but it's a asymptotic Markov measure. Okay?
Excuse me, so here beta n does not depend on x tilde, or z?
X tilde have to be of the same size, that's all. Whatever z is.
Okay.
Y is the same.
I just said stabilize.
Yeah.
Tends to 0.
It stabilizes.
Under the same thing. Why?
In fact, to understand the proof, you can take beta n equals to 0. Okay, it's more or less. Okay. Then now this is another property, I suppose that Kn is doubling.
So this beta should depend on x and xy.
No.
What?
You have some.
Beta n depends on nothing.
You have some sequence, and n depends on its length of y.
Of the length of y, yes.
So when y grows,
Yes.
so we obtain some number, and the limit you obtain something. It depends on x and xy, of course, because you can have
Yes,
x
if you take two z that have the same,
or 2z
Q.
or 2.
so two points are being linked with the same sequence, then you put
z. I think it depends on x and x.
This is the supremum over all x's.
Oh, okay, good. So proof doesn't.
it's for
And this
yeah,
supremum is
so
supposed to be bounded, and this is the exact assumption.
then it makes sense.
The supreme over X. And then I suppose that the measures are doubling with
Is K negative?
no should be value of log.
This is
And just
Negative, yes.
yeah, because you have a smaller set, so your measure
It's
case. So that's just doubling.
Yeah.
Now, yesterday, just before I sent the slide, I don't know why I added this condition. I don't know. I was going back to the proofs and said I need this, and then finally,
Okay, so what's it?
after so forget this condition. Just the end beta goes to 0.
I think it is weaker than Helder continuity. So you want
Yes.
to bounded distortion, something like this. You can replace Helder by the weaker condition. So beta n is kind of distortion.
So,
So this is,
sorry, forget about it. Just beta goes to 0. In fact, in what we do, we'll have this property. But
so we have two measures now, yes?
you have two measures, okay? So,
And they both satisfy the previously.
No, one is conditional. No. Two different levels.
yeah,
But
no.
they both satisfy.
This
each other.
needed, sorry, the new measure needed the probability measure, but never mind.
It's you, another is logarithm.
Just a second, I will explain now. May I? This, in fact, this new would be related to the, could be just new, in which case we have entropy, or diameter of some of the cylinder, which would give us the amount of exponent. Okay, that's why.
No, the question was what's the meaning of these brackets?
As I said before, that's the sum over all x's of the nth generations of. Sorry. Yeah, right here. The best. So I take the sum over of mu of xy over mu of x log of mu of xy over mu of mu, sorry. Yeah. Mu of xy over mu of x.
And the sum is over all y's of length m?
And the sum is over all y's of length n. Yeah.
And the second?
Okay. And the second is over or all
Your point?
this is our stuff. Okay.
So on the right, minus 1 over n sigma mu of y.
Mu of y, yes,
Yeah,
yes,
of
yes.
y.
Where here?
Yeah, there's y and y is the best.
No, 6.
Okay.
It doesn't matter.
No,
It's
you have
okay.
x fixed.
No, because there's a coincidence of.
No, okay. No, this was.
No.
I didn't change anything. I just put it in place. Okay, sorry. Tell me.
X is fixed there,
Yeah, it is.
so you need some over
So
something
it
else.
cannot serve as a running parameter in the second sum.
It should.
Why would
Ah,
that?
okay. Sorry.
Why?
Call it. Okay, Z. Okay. I don't call it Y because Y is absolutely
Okay.
So that's the first thing, and then the second thing is that this same quantity here, okay, 1 over n. So okay, the entropy some state n minus 1 over n times log of nu of x n of x. This goes to 0, it's the second quantity, mu 0, which is almost as saying that the dimension is given by entropy, in some sense. Whatever limit infimum has this one will have it also. Whatever limit supreme has this one will have it also. Even better, if you have a subsequence for which this converges, this one converges also, mu is sure. Now, this is the main theorem, okay? This is the main, at least the main lemma, the main. And I will try to explain this. Once you get this, whatever follows is easy. Now, somebody would probably have the question, which would be a very natural question. Here we have cylinders of size n, but here we have cylinders also of size n, but are somehow lower. That is, with some things here and some things there. But when you go to the infinity, this part will disappear. Now, if you have proved this, if you have proved the second one, then of course we apply with mu the diameters, we get the Lyapunov exponent, and we apply with mu, and we get the.
Is PS French for almost everywhere?
Yes, it's almost the same.
Sorry. I speak some French, but I don't know almost everything.
You're almost okay. I tried to take all the French expressions out.
The previous slide name was perfect. Perfectly understandable.
So, and of course, we have something very beautiful here. How this limit infimum will be some constant d, and then the Hausdorff dimension will be d, of course. And then if you have the limit supremum of this same guy, you have the packing dimension. So, this proposition is a key. Now, this is with, in fact, one measure of the measure mu. Mu was either mu or diameter, so all this concerns one measure. Now we have to compare two Hausdorff measures, okay? So we have to show that when you have two Hausdorff measures, you have some kind of distance you have to put in place, okay? It's a natural distance here, and sorry, what's this? Okay, yeah. So, okay, have to it's correct, but no. That's the notation for me. So mu x of a, that's mu of x a over mu of x. Okay. So
we
what we want
one
here.
digit on because the length of A is equal to 1. So
Yeah, we want that every time you go from a father to a son, for this measure, to have the same ratio, almost the same ratio, as for this measure. Okay? Almost the same ratio. Saying that the metric is close to 0 means that when you go from the father to the son, you distribute the measure the same, almost the same way. Now, and this is the second thing. If you have measures that satisfy the condition we said before, that is the almost Markov property, and if they are doubling, then we have that this guy, the entropies are close, okay, the difference to the entropies of the, how to say, the nth stage, the nth step entropies go to 0. And of course, this would mean that the dimensions are the same. Yeah, this would mean that the dimensions, that is, sorry, sorry, the 2 and the 3 is just a resetting of the first one, because it's a corollary of the first one, okay? If this difference goes to 0, of course, they have the same limit infinite with the same limit supreme. If this difference goes to 0, the limit inferior of this sequence will be equal to the limit inferior of this one, and the same for the limit superior. If two sequences are close, but the limit inferior are close and the limit superior are close also. So the 2 and the 3 is a subsequence, it's a sequence of 1. Trivial sequence of 1. Okay? Nevertheless, of course, this will give us the dimensions are, well, this one will give us the dimensions are close, and the theorem is proved. Okay? Will be proved. Oh, okay. Okay, let's go back. That's good with, if I had just a black border to go back. Yeah, okay. So, what we said here, sorry, we said that under this condition, okay, the main lemma, this limit infimum is irrational. Okay? The entropy divided by the exponent will give us a dimension in some sense of limit inferior. Now, what I'm saying is that if you have two measures that are close, okay, then take here mu and here mu tilde. Okay? In place of mu, put mu tilde. If you put mu tilde instead of mu, here you get that the entropies are close. Okay? If you put the diameter here, you will get that the Lyapunov exponents are close. So, since the ratio entropy over Lyapunov exponent will give you in the limit inferior the dimension of mu, and the same ratio will give you the dimension of mu tilde, and since these are close, the dimensions of mu tilde are close also. I'm not convinced. What said the previous theorem is that this is the limit infimum of hn of mu over cn of mu. Okay? For mu tilde, of course, the same thing. If we admit the proposition, this first, sorry, take this formula here and replace mu par mu and mu tilde par mu tilde. Then you have that the two, mu par mu and mu tilde par mu tilde. This means that the sequences here that give you the entropy, this and this one, are close, epsilon close. Okay? And if you place uniform diameter, it means that the sequence between Kn are close. So the ratios are close. So these dimensions are close. Okay. So I have two propositions to prove it to you. At least try to prove. The first one is to say that is this one. And the second proposition is to say that when mu and mu are close, I have this for the entropy set, same thing for the recommendation. And I have that now. Yes.
I think you have to convince the audience that harmonic measure satisfies the assumptions of your proposition.
Yeah, of course. I have to show that they satisfy the assumption and that the propositions are true. For the assumption it's easy. Because it's easy because somebody else has already done it. Okay? I stopped it a few minutes ago. Yes. Okay, I will start with, because Anna changed the order of the things.
No, but
I will start by, so that, so,
just notice that the proposition is general, so it doesn't
Yeah.
say anything about harmonic measure, just.
so I will start with this. I never say no to Anna. That is something that I learned a long time ago.
That's very wise.
What did you say?
Age. So, take an autonomous or non-autonomous conformal IFS, this is true for all IFS. There exists some constant Q and C, Q smaller than 1, that make this inequality true for all x, for all z, and for any cylinder of length k. Just the only thing we have to keep always in mind that we cannot put the one under the other any cylinders. We have to have a meaning. This has to have a meaning. Okay? But this proof is essentially a restatement, almost, of a beautiful remark that is in my memory in Carlson's paper, and then it was rewritten more generally by McCarthy in 1986, that says that whenever you have two positive harmonic functions, and we have a system with annualized, which is our case here, with annualized, when you go down the annualized, the ratio of the two, the functions are supposed to be 0 outside the first smallest disk of what is annualized. There is an error here, which is perturbing. So the functions are supposed to vanish outside the A1. Okay? Now, you take x somehow far away, so we take x outside this annualized, okay? And then this ratio is stabilized, in fact does not depend on x, once you have taken x. So then that's in fact a very beautiful and tricky application of harnessing inequalities.
Yeah.
So now I'll try to explain how we get this. I told you the formulas are horrible, and I keep my promise. So now remember that when you fix a set on the boundary, this harmonic measures a harmonic function on x, and it's so easy. Of course, this v cylinder. And now, if we apply this this remark we talked about, don't show me, show the. So this guy will stabilize once we're outside. So to fix ideas, take this guy to be XYZ and this guy to be XY, okay? And then you have all this, you have a first annulus here, sorry, and the second annulus here, of course, others follow. So you can reasonably apply the theorem of Crash-Macaulay-Wolver. So this guy stabilizes from the far away, and then that's the tricky thing. If it stabilizes, so imagine that when x is here, imagine that when x is on this perimeter here, the ratio is stabilized, then you can cut out infinity and say I'm looking to the ratio inside this bigger domain, and the ratio will not change. See? It's just yeah, okay. Hans principle, maximum principle for those four elements, standard things. It's not surprising. Okay?
I have a question. So for this to hold, is it important that the images of your contractions do not intersect?
Yes. But even if they understand, if you're away from the boundary, one generation after, get things that not understand. You know what I mean? So you can certainly, I'll say, lighten the hypothesis. Here you have to have this angular. If you can get it in some way. Now, why did I put the whole thing in a bigger disk? Because for the moment where I put it in a big disk here, if I take a copy of the set elsewhere, a conformal copy, Hausdorff measure is easy, conformal invariant. So whatever happens inside this area will happen in all copies in Hausdorff set everywhere else. Okay? So and then I can once more, this is broad formula, take out this disk and reconsider things in C. We will not change a thing. So after all, if you do this game, go inside, close it, take it conformal somewhere else, you have the same things, and then unwrap. You have managed to compare, so this is a C, it's an error here also. You have managed to compare what happens in two different cylinders, inside two different cylinders. Now, we just showed that harmonic measures satisfy the
Assumptions.
the assumptions, the transmission values. Now, let me prove this property now. Okay, this proposition. Okay. You really forget it. Use this. Keep this in mind, okay? This formulation. And in fact, even this would be. Now, I will use a variant of the law of large numbers. What we know is that when we have identically distributed and independent normal variables, we have that 1 over n sum of xn minus the mean value goes to 0. Now, in our case, what I want to do is I take it to police 8. This police 11. So what I want to do is I have this kind of things here. Okay? So if you look, this thing, it seems as if it is a conditional expectation, okay? And this guy here, you can write it as like this, log of x1, mu of x1 I1, let's say, in over mu of xi1 in minus 1 times what am I saying? Sorry, xy times mu of xy i1 in minus 1 over mu of xy in minus 2 and so times whatever will be the parameter. Okay, a finite mu of x. So this guy here, sorry, I can write like this where I have decomposed y in the sequence of digits. Okay? And of course, if I take the sum of this, if I'm looking at this guy is the sum of the logarithms. Okay. So what I see here now, I see random variables, and my random variables are that log of x of x of the sum of something over the father of something, and I assume this is logarithms. Okay? So this guy here is a sum of random variables, and if you look at it very well, these are some of random variables which are whose we take the expectation with respect to the previous relation. Okay? Now, okay, let me see. Just a small second. Yeah, that's what I wrote here. Okay, so Zn can be written as these random variables. Okay, the sigma algebra I'm talking about is this one. So if you take the expectation, you get exactly this kind of thing. Okay. Now, what is also true is that this is true from when you go from x to y. if you want to go from X to several Y's, just have to add them. It's all to take Windows. You superpose Windows and get exactly what you want. Now, the random variables we have created are bounded because of the doubling hypothesis. And in fact, this theorem you can find in the Gordon Heider are it's much more general. Okay? I have written.
So here in the summation, index I corresponds to the length of a cylinder or to something else.
It's exactly as I showed here. That's the eyes here. You just have cut Y's in subcylinders. Okay. Now, okay. In fact, what happens now? The subcylinders are not of length 1, are of length P. Is what we are doing, okay? I have to have P big enough, but fixed. So, the main issue, the main problem here yeah, it's horrible, but it's even more horrible than the article, believe me. Now, don't look at this, look at me. So, okay, what's the main thing to do? We know, after what the previous thing, we know that if you want just 1 over n, let's say it like this, I use usual notation, okay? This guy minus the entropy I know that these guys go to 0. Almost everywhere. That's what the theorem tells me. Okay. The theorem, the probabilistic theorem, gives me this. And
wait, so you cut into cylinders of length P to get this beta and RTI. I'm sorry, I don't remember the name.
no, yeah.
So if we use the beta equal to 0, we could just cut into cylinders of like what, length 1?
No,
2 perhaps.
it will not work.
Okay. Okay. So
even for Markov measures, this is not an element. You cannot kind of do because you have length 1. At the right you have one distribution, at the left another distribution. Markov, the father decides for the distribution of sums, so it depends on which one is your father.
okay. So it's used. Okay.
Even for Markov distribution, it's not clear, but it's easier, but not clear. Now, keep this in mind. That is, this will give us this one, and this will give us this one. Almost. Why almost? Because here you have conditional expectations, and of course, if you sum them, you cannot get something like this. You just get other random variables that are just mean values of your first random variables, but in a large window. And there where your Markov property comes to say that if you take the window sufficiently large, sufficiently big, these guys here will be stationary, not stationary, but will be equal between two windows. Okay? And this really is not trivial. It's elementary as proof, but it's not trivial. Okay? And the only way I could do it, I'm not brilliant, but I spent some time on it, is to go by contradiction and go back in the generations to verify the contradiction, suppose that it's not true. Never mind, this is not true to say that when you have two windows, you do the mean values far enough, they stabilize between them, at least not in general. We don't have any limit, but we have this almost spherics conjecture. So now once you have this, once you have this means now that this guy does not depend on x. So you got your what you want. Now that was the first problem. The second problem now, sorry, not yet. Poor things. If it was over. So we have proved that the measures, harmonic measures, satisfy the hypothesis, and we have proved the proposition 1, which says that I can get dimensions through some kind of entropy and Lyapunov exponent formulas. But I didn't prove that when the Cantor sets are closed, that is, when the IFS are closed, the harmonic measures will be closed also. Okay? The fact that the Hausdorff dimension will be closed, this is the work of Marius and other authors. Now we're speaking about just harmonic measures. Okay? So, what I am doing in this slide, I will just give you a sketch of the proof of the fact that when you have two non-autonomous IFS that are closed, harmonic measures will be closed, dimension closed. Okay? Sorry, they will be closed. That we will have what? Omega tilde of x, y over omega tilde of x divided by omega of xy over omega of x. And this is almost 1. Okay? 1 plus minus epsilon. That's what I want to prove. But because if I prove this, then I have a control. Then I get a control on the entropies, and there is just a big job to do to say that the entropies will be closed also, which is not clear at all. Okay? And then we'll finish the proof with the previous proposition. There are many steps in the proof. This is a step that's easy to explain, so I will try to explain it at least. So we have our. This is the first Cantor set, okay? And I will try to put the second, but after I will have said something. The hypothesis that the conformal maps do not shrink too much give us some high capacity property on the set, okay? Which can be translated in harmonic measure in the following way. If you want harmonic measure of x to some cylinder, let's call it x, to be big, but you just have to get x close to the cylinder. Okay? That's what the high capacity will give you. If you are close enough to the cylinder, then harmonic measure will be big. Now, of course, if you have a cylinder, this depends on the size of the cylinder, because if you have a cylinder size 1, it's okay. If you have a very small cylinder, this epsilon will go to 0 with the size of the cylinder. You can take 1 minus epsilon times the diameter of the cylinder. Never mind, the main idea is this one. If you are close enough to the cylinder, then you're okay. Now, the second idea is the following. I'm interested, is this ratio. Okay? If I'm interested in this ratio, suppose that x is big, for x smaller there is no problem, but for x big, I can cut x in two parts, okay? The first window and the second window, both of them will be x, okay? Now, by the McCarthy-Carlson remark and our proposition that goes with, this ratio does not depend on x1. If x2 is sufficiently big, the y we used before, this will be the same, never mind who x1 is. And the same thing here. So we have our big X, our Y, okay? But the big X is not totally useful. I may cut off the best, the biggest part of it. Okay? So using this theorem, I can just work on finite windows, finite length. And if I work on finite length windows, let's say the first one, so it's the same thing, the first piece test. Then I can use this to say that, okay, I get the level set of the function, the 1 minus epsilon level set of this function. So I get something like this one. This is the level set here, here, I don't know where it is, here, 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 here. These are my level sets, okay? When we're inside the red line, the value of omega is bigger than 1 minus epsilon. And now what I have to do is take the contractions to be close enough, that is, the second IFS to be close enough to the first one, in order for the cylinders of the second to be inside of this red line. Okay? And if I reset the red line, what do I have? I have that for the one measure, here I'm even more than 1 minus epsilon, but for the other measure on the blue lines, I'm in 1. So I have the same value almost. By the maximum principle, this is true everywhere. So it's okay. So having one inequality, you have to take each of those. In that sense, we have the other inequality. So this proves that if the contractions are close enough, the IFS are close enough, the harmonic measures satisfy this property, if they satisfy this property, I get that the distance, I get that the dimensions are close, and that's what I want. Now, that was the trick. I hope it was a trick. I took that time to do it less complicated than it is. And I don't know how to pronounce it, but I found it.
Questions?
I have a question. Do you know counterexample to the statements in the case when you allow switching? For instance, if you have parametric family of IFS monotones, such as in the limit that they touch
Yes.
them.
No, I don't know. That is, the fact that you can see there are two ways to work with to create the added line. One is to say that they don't touch, so you have the added line naturally. And the other way is to say that they are far away from the bottom. So the next generation just separate the end. Now, if both of them don't work, I don't know what happens. I don't know. They have no intuition.
But if you are separated from the border, it's to the zero.
To write it down is a bit more harsh.
But do you need that in the limit you get Cantor set, or what's about it? So if it's not Cantor set, it's problematic? If it is not Cantor set in the limit, it's problematic to work with it?
Yes.
It's like a Julia set in
In fact, there are many things that you imagine right, but they are not. Okay? You imagine if you have a counter set in the real line, the third counter set in the real line, you know that, of course, the dimension of the function is not the dimension of k. But a remark we did with Anna last time was here, which a very funny remark. Take a counter set that is slightly different. So suppose I cut in 9 here and 3 here, and take this one, this one here, and this one, and start over. Okay? Something here, something there, etc. So whatever you get here will be a graph of a function. And it's even funnier, increasing function. So bound variation for the unit. And so you say like that. That's a counter set. It seems rather normal that harmonic measure and the Hausdorff dimensions are the same. But in fact, not only the dimensions are the same, but the two measures are equivalent in this case. Which is very funny.
So just to make this into conformal IFS.
Yeah, that's one iteration we were working on. I still wait for the him to give the proof, but yeah, the limit is a very interesting question. What happens is that when the ratios, the contractions go to 0, we would expect to have similar dimensions. Questions? I did.
I told you.
Then I also have a question from online.
I will answer offline. Okay.
Offline. So if you could go back to this key proposition on the almost sure convergence of a logarithm of one measure with respect to another one. Yes, here. Point 2.
Yeah, this one, okay.
So maybe first I have a small comment. So this second point that you prove, it seems to be a non-autonomous version of a classical result in information theory, which is called
That's what I'm saying. That is it's exactly what I proved, tried to prove in the using this mathematical formulation, this probability formulation.
Yes. Yeah. So this quantity on the left, it's sometimes called relative entropy or the Kullback-Leibler divergence.
Yes.
And as you have shown us, it is useful for applications to harmonic measures. And I wanted to ask whether you are aware of some other families of maybe these non-autonomous measures to which you can apply this machinery.
To start with,
so basically, yeah.
Yes, tell me.
So some other classes that satisfy also these assumptions that you have here.
In fact, in all reasonable measures I can think of on these non-autonomous counter sets, That is, if they have something to do with the sets. Okay, if not, you can put a uniform measure in symbolic set it back. That doesn't mean anything. They have to have this translation invariance. That's the main idea. You say non-autonomous means that whatever you do here, at the same generation, you'll do it there. So the measure has to have this quasi-translation invariance also. And that's why, from the moment you have this translation invariance, even mildly, this works. But yeah,
So,
if you want.
so things like infinite product measures, maybe with some control on how the probabilities change.
Yes, it works. We have already done this. Yeah. If probability measures.
Okay, thank you.
Thank you, Adam. See you next time.
Thank you.